In this lesson, we're going to look at another common type of sequence called the geometric sequence. We'll learn how to write a geometric sequence recursively and explicitly, and we'll learn how to find partial sums of a geometric sequence. So remember that an arithmetic sequence is a sequence where the difference between one term and the next term is constant, that constant being called the common difference. A geometric sequence is a sequence where each term is found by multiplying the previous term by a constant, called the common ratio. So I first want to make a quick visual comparison between the graph of an arithmetic sequence and the graph of a geometric sequence. So here we have an arithmetic sequence where the first term is 1 and our common difference is 2. So we'll say that our first term starts at 1 and the next term increases by 2 and the next term increases by 2 and the next term increases by 2 and the next term increases by 2. So here you can see that an arithmetic sequence just makes a straight line, and if a line were connected through these dots, you'd have a linear function. So now we'll take a look at the graph of a geometric sequence where the first term is 1 and the common ratio is 2. So if the first term were 1, we could plot that here. Now the next term is the result of the first term being multiplied by the common ratio. So if we multiply the first term by 2, then our second term is 2. Multiply this term by 2, then the next term is 4. Multiply this term by 2, and our next term is 8. So you can see if we were to connect a line through this set of points, a geometric sequence would not represent a linear function, but in fact it would represent an exponential function. So for this first example, we're going to take a look at two sequences and first determine if they're geometric, and if they are, then what is the common ratio, and then we'll write each sequence as a recursive function. So to determine if a sequence is geometric, all we need to do is look for a common ratio. That is, take any term, divide it by the term that comes before it, and see if that is the same as every other term divided by the term that comes before it. So 9 divided by 3 will give us 3. 27 divided by 9 will give us 3. And 81 divided by 27 will also give us 3. So this is in fact a geometric sequence where the common ratio is 3. Now to write this as a recursive function, we need to say that any term in the sequence is equal to 3 times the term that comes before it, with the first term being equal to 3, and this is true for all values of n greater than or equal to 2. So again, for sequence B, we just need to determine if there's a constant ratio between every term in the sequence. So notice half of 5/2 is 5/4, and half of 5/4 is 5/8, and half of 5/8 is 5/16. So each term is being multiplied by 1/2. So this is in fact a geometric sequence where r is 1/2. So to write this as a recursive function, we'll just say that every term is 1/2 times the term that came before it, with the first term, u sub 1, being equal to 5/2, and this is true for all values of n greater than or equal to 2. The recursive form of a geometric sequence u sub n is given by u sub n is equal to the common ratio times u sub n minus 1, and this is for some u sub 1 and some non-zero r, and all n greater than or equal to 2. So in this example, we're going to start with the first 2 terms of a geometric sequence, and then we're going to find the first 5 terms after finding the common ratio, and then write the sequence as a recursive function, and then we'll look at the graph of the function. So to start, to find the common ratio, we just need to take u sub 2 and divide that by u sub 1. So that's 8 divided by 2, which gives us 4. So we know that our common ratio is 4. Now to list the first 5 terms of the sequence, we'll just start with the first 2, u sub 1, and then u sub 2. The first 5 terms, well, every term is 4 times the previous term, so 4 times 8 is 32. 4 times 32 is 128. 4 times 128 is 512. So here are the first 5 terms of this sequence. So next we're going to write the sequence as a recursive function. So we'll start with u sub n representing any term in the sequence, and that's equal to 4 times the term that came before it, with the first term being 2. So we'll say with u sub 1 being equal to 2, and this is true for all values of n greater than or equal to 2. Next, we'll take a look at the graph of the function. So here you can see that the first term is 2, the next term is 8, the next term is 32, the fourth term in the sequence, notice we're past 100 now, the fourth term is 128, and the fifth term is 512. In this example, we'll confirm that sequence u sub n, which is defined recursively, can also be expressed in this form, which is the explicit form, by listing the first 7 terms produced by each form. So, using the recursive form, we know that u sub 1 is equal to 7. And then if we continue multiplying that by the common ratio of 2, we'll just get our first 7 terms. So, u sub 2 is equal to our first term times 2. So that gives us 7 times 2, which is 14. Now u sub 3, that's equal to u sub 2 times 2. And that's equal to our first term, which was 7 times 2 times 2. In other words, this is 7 times 2 squared, which gives us 28. Now u sub 4, that's equal to the third term times 2. Well, our third term was 7 times 2 squared. Now we're going to multiply that by 2, so this gives us 7 times 2 cubed, which is 56. U sub 5, well, that's our fourth term times 2. Our fourth term was 7 times 2 cubed. We're going to multiply that by 2, and that's going to give us 7 times 2 to the fourth power, which is 112. U sub 6, that's our fifth term times 2. Our fifth term was 7 times 2 to the fourth power. Now we're going to multiply that by 2, so that gives us 7 times 2 to the fifth power, which is 224. And finally, u sub 7 is our sixth term times our common ratio. Our sixth term was 7 times 2 to the fifth power. We'll multiply that by 2, so we're left with 7 times 2 to the sixth power, which is 448. Well, notice that our third term was our first term multiplied by the common ratio twice. And then the fourth term, that was our first term multiplied by the common ratio 3 times. All the way up to the seventh term, which was our first term multiplied by our common ratio 6 times. So this shows that our sequence u sub n could also be written in this form: u sub n is equal to the first term multiplied by 2, n minus 1 times. So if u sub n is a geometric sequence with common ratio r, then for all n greater than or equal to 1, u sub n is equal to the first term times the common ratio n minus 1 times. So in this example, we're going to write the explicit form of a geometric sequence. So we're going to write the explicit form of the geometric sequence where the first 2 terms are 2 and negative 2/5, and then find the first 5 terms of the sequence. So since we're given the first 2 terms of the sequence, we can find our common ratio and say that u sub 2 divided by u sub 1 will give us r. So negative 2/5 divided by 2, well, half of negative 2/5 is negative 2/10, which is negative 1/5. Or half of 2/5 is 1/5. So now that we know that r is negative 1/5, we can write the explicit form of our geometric sequence. So we'll say that u sub n is equal to our first term, which is 2, times our common ratio, which is negative 1/5, n minus 1 times. Well, next we're going to write the first 5 terms of our sequence, and we already know that u sub 1 is equal to 2, and u sub 2 is equal to negative 2/5. Well, u sub 3, that's equal to 2 times negative 1/5 raised to the 3 minus 1 power, or squared. So that gives us 2 times negative 1/5 squared. Well, negative 1/5 squared is 1 over 25. That gives us positive 2/25. U sub 4, well, that's just 2 times negative 1/5 raised to the third power. So that's 2 times, well, a negative to the third power is still going to be negative. So we're going to have a negative 1, and then 5 cubed, that's 125. So we're left with a negative 2 over 125. And finally, our fifth term, u sub 5 is equal to 2 times negative 1/5 raised to the fourth power. So we have 2 times, well, negative 1 to the fourth is a positive, and 5 to the fourth is 625. So we have 2 over 625. So here we have the first 5 terms of our sequence. 2, negative 2/5, 2 over 5 squared, negative 2 over 5 cubed, and 2 over 5 to the fourth. So this example is interesting. Instead of giving the first 2 terms and asked to write the explicit form of a sequence, we're given the fourth and ninth term of a geometric sequence, 20 and negative 640, and asked to write the explicit form. So we know that our fourth term, u sub 4, which is equal to our first term times our common ratio to the n minus 1 power, well, our fourth term is 20, and that's equal to u sub 1 times r. Our n is 4, so 4 minus 1 will give us 3. Our ninth term is negative 640, so u sub 9 is equal to our first term times our common ratio to the n minus 1, or we can just write negative 640 is equal to u sub 1 times r raised to the 8th power. Now we can use these two to find our common ratio. So we know that u sub 1 times r to the 8th divided by u sub 1 times r cubed is negative 640 over 20. Well, u sub 1 over u sub 1, that cancels. R to the 8th over r cubed, we'll subtract our exponents and we get r to the 5th. Negative 640 divided by 20 is negative 32. So we just have to answer what to the 5th power is negative 32. Well, we know that negative 2 to the 5th power is negative 32. So our common ratio is negative 2. Now, in order to find our explicit form, we need to find the first term of our sequence. Well, we know our common ratio now, so we can just substitute that back into this formula and solve for u sub 1. So 20 is equal to u sub 1 times negative 2 to the 3rd power. So that's 20 is equal to u sub 1. Negative 2 to the 3rd is negative 8. Just divide both sides by negative 8, and we'll get our first term. 8's cancel. 20 over negative 8 simplifies to a negative 5 halves. Well, now that we know our first term and we know our common ratio, we can write the explicit form of our sequence, and we'll just write that here. U sub n is equal to our first term, negative 5 halves, times our common ratio raised to the n minus 1 power, and this is true for all values of n greater than or equal to 1. So remember that a series is a sum of the numbers in a sequence, and if we wanted to find the nth partial sum, we just add up the first n terms in the sequence. So suppose we had the geometric sequence 2, 6, 18, 54, 162, and so on. So in this case, our common ratio would be 3. 6 divided by 2 is 3. 18 divided by 6 is 3. So our common ratio is 3. Well, the fifth partial sum, or S sub 5, the fifth partial sum, would be 2 plus 6 plus 18 plus 54 plus 162, just the sum of the first 5 terms. Well, now here's a trick that we can apply to this equation that'll lead us to a formula that'll allow us to find the kth partial sum of any sequence. So what we're going to do is we're going to multiply both sides of this equation by the opposite of our common ratio. So we're going to multiply both sides of this equation by negative 3. So we're going to have negative 3 S sub 5 is equal to negative 6 minus 18 minus 54 minus 162 minus 486. Remember, these terms are just negative 3 times all of these terms. Now what we're going to do is we're going to add these two equations together. So s sub 5 plus a negative 3s sub 5 is just s sub 5 minus 3s sub 5. When we add the right side together, notice our 6 and negative 6 will just cancel out. So we'll 18 and negative 18 and negative 54 and 54 and negative 162 and positive 162. So when we add the right side, what we're left with is 2 minus 486. Well, on the left side, we have two terms, and there's a common factor of s sub 5. So we're just going to factor that out. So we have s sub 5 times, well, s sub 5 times 1 is s sub 5, and s sub 5 times negative 3 is negative 3s sub 5. On the right side, we have two terms, and both those terms have a common factor of 2. So we're going to factor out that common factor. 2 times 1 minus, and 2 times 243 will give us 486. Well, now to get s sub 5 by itself, we'll just divide both sides by 1 minus 3. So s sub 5 is equal to 2 times 1 minus 243 all over 1 minus 3. And there we have it. The fifth partial sum is equal to all this. Well, the 2 is just the first term in our sequence. The 243 is our common ratio raised to the nth power. So this is 3 to the fifth power. The denominator is just 1 minus our common ratio. So our formula to find the partial sum of a sequence is just this. S sub n, or the nth partial sum, is the first term times 1 minus r to the nth power over 1 minus r. So this is the formula for finding the nth partial sum of a geometric sequence. And the book writes it this way. So the kth partial sum of a geometric sequence u sub n with a common ratio not equal to 1 is the sum as n goes from 1 to k of our sequence. And that's just equal to the first term times 1 minus r to the k, or the nth term of our sequence, over 1 minus r. So in this example, we're asked to find the sum of the first 9 terms of this geometric sequence. So we're asked to find s sub 9. Well, to do that, we first need to find the common ratio. So we can take any term and divide it by the preceding term. So if r is equal to, let's say, the second term divided by the first term, which is a negative 3/2. So 3/4 divided by negative 3/2 is 3/4 times a negative 2/3. The 3's cancel, and negative 2 over 4 is a negative 1/2. Now if we wanted to write this sequence in its explicit form, we could say that u sub n is equal to the first term times the common ratio raised to the n minus 1 power. Well, to find the 9th partial sum of this sequence, we'll just use our partial sum formula. So the 9th partial sum is equal to the first term, negative 3/2, times 1 minus the common ratio raised to the nth power, so in this case 9, all over 1 minus the common ratio. Alright, so we simplify this and we'll end up with our 9th partial sum. Well, we have negative 3/2 times a negative 1/2 to the 9th power is a negative 1 over 512. So if we subtract a negative 1 over 512, we're actually adding. So subtracting a negative makes it positive. 1 over 512. Over 1 minus a negative 1/2. Well, that means, again, subtracting a negative, which means we're going to add, and 1 plus a half is 1 1/2, or 3/2. So now we have this fraction with 3/2 as our denominator. So we're dividing by 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So we can say we have 2/3 times a negative 3/2 times 1 plus 1 over 512. Well, these 2's are going to cancel. The 3's will cancel, leaving us with a negative. So we have negative 1 times a 1 plus 1 over 5/12, and 1 plus 1 over 5/12 is just 1 and 1 5/12. Multiply this by -1, and that gives us a -1 and 1 over 5/12, which is just -513 over 512. So the ninth partial sum of this sequence is -513 over 512. For this last example, a ball is dropped from a height of 9 feet, and it hits the ground and bounces to a height of 6 feet. It continues to bounce up and down. On each bounce, it rises to 2/3 of the height of the previous bounce. How far has the ball traveled both up and down when it hits the ground for the 7th time? So notice our initial height is 9, so the ball bounces to 2/3 of the original height, so that would be 6 feet, and it falls 6 feet, and then it rises to 2/3 of that, and then it falls that same distance. So we first need to consider how far the ball travels on each bounce. On the first bounce, it rises 6 feet and falls 6 feet for a total of 12 feet. And on the second bounce, it rises and falls 2/3 of the previous height, so it travels 2/3 of 12 feet. Now the distance traveled is a geometric sequence because every distance is 2/3 of the distance before it. So what we have here is u sub 1 is equal to 12, and our common ratio is 2/3. So if we let u sub n represent our sequence, then every term in the sequence is the first term times 2/3 raised to the n minus 1 power. So when the ball hits the ground for the 7th time, it's actually completed 6 bounces. Therefore, the total distance it's traveled is the distance it was originally dropped, the 9 feet, plus the distance it traveled in 6 bounces. So 1, 2, 3, 4, 5, 6, 7. So what that means is we have 9, our initial height of 9 feet, plus the rise and fall of those 6 bounces. So that would be u sub 1, u sub 2, plus u sub 3, plus u sub 4, u sub 5, and u sub 6. So we're going to find the 6th partial sum of this sequence plus the initial drop of 9 feet. So that means we have 9 plus our first term in the sequence, which is 12, times 1 minus, well, our common ratio is 2/3, 2/3 raised to the 6th power. This is all over 1 minus our common ratio. So this is 9 plus, well, 12 times 1 minus 2/3 of the 6th power comes out to be about 10.9, and 1 minus 2/3 is 1/3. So this becomes 9 plus, and it's about 32.8. So the ball travels about 32.8 feet in 6 bounces plus the initial height of the 9 feet for about 41.84 feet.